So this is going to be about expanding binomials, and all that means is that we're going to raise an expression of two terms, right? That's what a binomial is, to different exponents, and we're going to see what the result is. What you're going to see is that the higher the exponent gets, the more obnoxious and tedious the computation gets. And so our ultimate goal is to find a little shortcut, and that's what this is all going to be about. So I'm going to work out these first few here, and anything to the 0 power, I hope you remember as 1. Anything to the first power is just what it is. And now when we get to the second power, you have to remember that we're going to FOIL, or distribute. And so then what we would get here is a squared plus ab plus another ab plus b squared. And if we simplified that down, we would have a squared plus 2ab plus b squared. And so now when we add, or when we increase the exponent one more time, we're already getting to a fairly obnoxious point, because we're going to have to distribute a plus b into the trinomial that we just got. So then we would get a cubed plus 2a squared b plus ab squared plus a squared b plus 2ab squared plus b to the third. So when we combine terms, we get to a cubed plus 3a squared b plus 3ab squared plus b to the third. So I'm going to do one more of these, and so this would be ab, or a plus b to the fourth. And again, we're going to have to distribute another a plus b to all of this. So I'm going to spare you the talking. So this is what you would get if you distribute a and positive b to what we found for a plus b to the third, and this is what we're going to get when we combine like terms. So, maybe at that point you're saying, well, that's not too bad, but if we continue this on and on, what are you going to do if you're asked to do a plus b to the 10th? There's just a lot of places to make a mistake, and so what we want to look for here is a pattern. So I've written out the first 6 binomial expansions, and what mathematicians do a lot is just look for patterns, and so I kind of color-coded a couple things for us to take a look at. You don't want to have to keep distributing, and that's kind of why we want to see these things. And the first thing I want to look at here is what's going on with the exponents. Okay, clearly when we were at the first one, there was going to be no exponents at all. Okay, and then when we were at an exponent of 1, you don't really see much going on with the exponents. They are 1s, and so that's important. So now let's jump down to the second one. So now what you're seeing is the first term has the same exponent as the expansion exponent, and the last exponent, the last term, has the same exponent as the expansion exponent. And then these two both have a 1 up here. And so if you add them together, they are also 2. And so let's see if that pattern continues. So when we cube it, the first term is cubed. The second term has an exponent of 2 and then a 1, so those add up to 3. The next term has a 1, then a 2, and those add up to 3. And then the final one has a 3 again. So again, look down at the fourth step. We have a total of 4, a total of 4, total of 4, and it keeps going. And so there's a pattern right there that we can look at. 5, 4 and 1 is 5, 3 and 2 is 5, 2 and 3 is 5, 1 and 4 is 5, and 5. So one of the patterns that we can recognize here is that every term, the sum of the exponents in that term is going to be the same as what our expanded exponent is going to be. The other thing to notice about the exponents is that the first term in our original, as we go across, as we go across, it decreases by 1. So on this 1, a plus b to the second power, it started as a 2, the a started as a 2, it went to a 1, and then it has a 0 exponent now. Okay? Down here, when we raised it to the third power, a started as a 3, or the exponent was a 3, then it became a 2, then it became a 1, and then it was gone. A plus b to the fourth. The a had a fourth power, then it had a third power, a second power, power to the first, and then it was gone. Okay, and so if we look at the b's, it's going to do the exact opposite, right? It's going to start at 0, go to 1, to 2, to 3, to 4, to 5. Right? When we take the next step, b has an exponent of 0 in this term. Then it goes to an exponent of 1, an exponent of 2, 3, 4, 5, and 6. Okay, so two things to keep in mind here. Okay, firstly, the sum of the exponents in each of the terms is equal to the original exponent in the question. And I couldn't figure out a better way to say that, right? Every term in the 6th row expansion, or I guess it's kind of the 7th row expansion, every one of these exponents in these terms are going to add up to 6. 6 plus 0, 5 plus 1, 4 plus 2, 3 plus 3, etc. So the second part of the pattern that we should see with exponents is the first term's exponent decreases by 1 as you move down the line to the next term. Right? The a is the first one here. It went from 6, 5, 4, 3, 2, 1, gone. The second term's exponent increases as we go. 0, 1, 2, 3, 4, 5, 6. So let's look and see if we can see any other patterns, and I've highlighted the coefficients as I go, and I've intentionally set them up to look like this triangle. So the coefficient is just 1 here because the whole term turned into 1. And then in the second entry, right, the power to the first, both exponents are 1. Then it goes 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, and you can read it out, and you see how they go. And so there's actually a pattern that's going on here. And so I'm going to go to the next slide. I'm going to get rid of all of the other symbols except for the coefficients. So this is what that triangle looks like without all of the variables and addition signs. And this is called Pascal's triangle, and Pascal was a mathematician that was alive in the 1600s, and he was very influential in not only math but in the physical sciences as well. And pretty interesting guy. At 16 he was writing textbooks on geometry, so pretty bright guy, and he noticed this pattern going on, and we're going to apply this. And again, this is called Pascal's triangle. You're going to want to know how to create this. And then I'm going to show you how it will help us. So this is Pascal's triangle. And what you want to see here is how it's created. The first one is a 1, and the next two are 1s. And then what you want to look at is, right, how do we get from the second row to the third row here? Well, we start off with a 1. 1 plus 1 is 2, and then we get to another 1. All right, so we move down. We just drop down the 1. 1 plus 2 is 3. 2 plus 1 is 3. and then we drop down the next one, right, down to the next line. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then we drop down the 1. Right, drop down the 1. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and we drop down the 1. Right, drop down the 1. 1 plus 5 is 6, 5 plus 10, 15, 20, 15, 6, and 1. So if we want to make the next line, right, you're going to drop down a 1. Oh, that's a pretty, why did that happen? So then we're going to drop down a 1, and then 1 plus 6 is 7. 6 plus 15 is 21. 35. 35 again. 21, 7, and 1. And so what that tells us is that our next entry into our expansion, so for instance, oh my gosh, what's going on? Right, this would be a plus b to the 7th. We would know that our coefficients would go 1, 7, 21, 35, 35, 21, 7, and 1. And so that's the other pattern that we're going to use, and we're going to use this along with the exponent ideas to expand some binomials. So you're going to want this triangle handy, and in fact it's going to be one of your all's quiz questions, so just know how to construct the Pascal's triangle, because then when I ask you to expand a couple of these, it won't be a big deal. So let's just use this row to figure out what a plus b to the 7th is. So we would know that the first term has an exponent, or a coefficient of 1, and it'd be a to the 7th. And then as we move down, it would go plus 7 from our Pascal's triangle, a to the 6th, b to the 1st, right? We got to remember those exponent rules as we go. Plus 21, a to the 5th, b to the 2nd. Right? They all have to add up to 7. Plus 35, a to the 4th, b to the 3rd, and so on. I'm going to run through some examples for you, and I'm going to change it up a little bit. I would not try to do this without first writing down Pascal's triangle. Now, I don't have enough room on here to write both the triangle and the work and actually have it on the same screen. So I'm just looking at a piece of paper right now while I'm doing this, where I've written out Pascal's triangle to the 10th line, and I'm just going to use that as my reference. So the very first thing you should do when you're doing these problems is to just write down Pascal's triangle. It'll make your life much easier. And so instead of using both variables, I'm going to use an integer here. So we have x plus 3 to the 5th power. And so I'm looking at Pascal's triangle. It's the 6th row. And I'll write down so that we can all be on the same page. The 6th row, right, would be 1, 5, 10, 10, 5, 1. Okay, so, get that triangle, learn how to create it and then just create it, and then anytime you need it, it makes sense. So, again, I'm going to just run through this, and it's going to be a little bit different. We're going to have an extra step here because instead of a variable, we have a 3. But the first term is going to be 1x to the 5th, plus the coefficient is going to be a 5 now, x to the 4th times 3, plus 10 x to the third 3 squared, right? These exponents still add up to 5, plus 10x squared 3 to the third now, plus 5x 3 to the fourth, plus 1 times 3 to the fifth. Okay, so it was the same pattern. Nothing was different from anything I've shown you so far, right? The first term here starts with an exponent of 5 and decreases to 4, to 3, to 2, to 1. Now it's gone, right? The second value here, the second term in this expansion is a 3. It starts out not being there. 3 to the first, to the second, the third, the fourth, the fifth, right? The sum of all of our exponents in each term add up to 5. Okay, and then I just took the coefficients from that row of Pascal's triangle. Now, of course, we have to simplify this, and so this is what we would end up getting. Right, we'd have x to the fifth plus 15x to the fourth. 3 squared is 9. 9 times 10 is 90 x cubed. Plus 3 to the third power is 27 times 10 is 270 x squared. So 3 to the fourth is 81. 81 times 3 to the fourth is 81. 81 times 5 is 405. X plus 1 times 3 to the fifth, which is 243. So x plus 3 raised to the fifth power expanded out is this. And you know, that's a lot easier to know this little trick than to actually FOIL x plus 3 by itself 5 times. So now there's a little curveball in here, and instead of an addition sign, we have the subtraction sign, but that's an easy fix. We're just going to think of this as actually x plus a negative 2 to the seventh. And I rewrote the line of Pascal's triangle that I'm using here, and we're just going to plug it in. You know, all our exponents have to add up to 7, so the first term is going to be 1x to the seventh, and then we're going to go down the line, plus coefficient of 7, x to the sixth, and now we're going to introduce the negative 2 to the first, plus 21 now is our coefficient, x to the fifth now, negative 2 to the second, plus 35 as our coefficient, x to the fourth, negative 2 to the third. Then we're at 35 again, x to the third, negative 2 to the fourth. Plus 21, x squared, negative 2 to the fifth. And then I'll drop down here, plus 7, x, negative 2 to the sixth, and finally plus 1 times negative 2 to the seventh. And so now all it is just doing your order of operations correctly. So make sure you're squaring a negative 2 when you need to square it, or raise a whole negative 2 to whatever the exponent is. And so it finally should simplify down to x to the seventh, negative 2 times 7 is negative 14, x to the sixth, right? Then we're on this term, negative 2 squared is positive 4. Positive 4 times 21 is positive 84, x to the fifth. Down to negative 2 raised to the third power is negative 8. Negative 8 times 35 is negative 280, x to the fourth. And then we keep going, and I think I've done my computations all correct, and so this is what you should end up getting. But again, just check your order of operation and watch your signs when you do this. So for the last example I'm going to do, made it as complicated as you're going to see. And the row I'm going to use from Pascal's triangle is 1, 4, 6, 4, 1. And now we just have to keep everything straight. And so if we expanded 2x plus 3y to the fourth power, we would go about it like this. We'd have the exponent of 1, and then it'd be 2x raised to the fourth power plus, I'm sorry, this is a coefficient. I said exponent. Coefficient of 4, and now 2x to the third power, and now we're going to bring in the 3y plus coefficient of 6, 2x to the second power, and 3y to the second power, plus the coefficient of 4, 2x to the first power, 3y to the third power, and finally a coefficient of 1, and then 3y to the fourth power. And now it's just about order of operation again. So we're going to raise 2 to the fourth power, and that's going to be 16. So our first term is going to be 16x to the fourth. And I'm going to write these out in a couple different steps. So plus 4 times 8x cubed times 3y plus 6 times 4x squared times 9y squared plus 8x times 27y plus 81y to the fourth. And then our final step, we're just doing some multiplication. We get 16x to the fourth plus 96x cubed y plus 216x squared y squared plus 216xy cubed, and finally 81y to the fourth.